All right, we're back for day 24 of Advent of Code. Here we go. Okay, I see AND gates, OR gates, XOR gates. Ooh, interesting. We have a giant combinatorial circuit, I think. The wire is starting with Z. Okay. I think this is pretty straightforward, maybe. Wait until both inputs are received for producing output. No loops. Cool. Yeah, so I think then we're just going to do we have some initial inputs, I assume. Let's parse the initials. And then I guess we'll just do this. And I think what we can do okay. Are they always 3 digits long? I think they are. Let's do this. This is a little silly, but I want to easily extract the left input. So, oh no, we can just split on spaces. That's much easier. Okay, that seems fine. To find the output of something, then what we're going to do is just like the following. Seems fine. This should just be fine, right? I think this is just fine. Let's not return it. Okay, seems good. Then now what we'll do, starting with Z. Okay. We probably want them like numbered, so I'm just figuring out the bit order. This is the highest order bit. Okay. I think we want this reversed. Yes, and then that's fine. What did I type? Not great. Oh, there's just a thing at the end. It's an empty new line. I don't really know why this is not quite getting it, but oh, I want gates. Oops. That's not great. A, B, op. A, op, B. Oh, wait, what did I do here? Ah, jeez. Silly bug. Oops, not sorted. Why did I try and do dot sort in place? Okay, there we go. Rank 135. Oh, so close. Let's try to add two binary numbers. Initial values is one instance of a pair of numbers. Oh, man. That's a little tricky. I don't know exactly how to approach this. Maybe like brute force it. That seems unlikely. They do give us a nice sample input here. Okay, so oh, well, this one's finding a bitwise and. Ours is an adder, right? Let's just look at it. How deep is this circuit? If only I knew how a combinatorial circuit that adds things worked, then this would be a lot easier. So it's this or this, which is the AND of these. This is the XOR of these. Okay, maybe we can start with like the lower order bits and then think of it from there. Let's try that. This feels very manual and I'm not really liking it. Either way, though, let's at least do the following. Let's figure out the X inputs. These should be in inits, actually. And then what we need to do we need to create a copy of G. GD we don't update, that's fine. We are modifying G though, and I don't want to put wrong values in there. Okay. we need to extract it. Yep, that seems fine. And then same thing for y. I guess technically it'll give us this ability. Y is not none. Y. Why do I feel like I type out something? I guess it seems fine. Okay. That's my part 1 answer. This is my part 1 answer. Okay. I'm not accidentally writing to G still, am I? No. What? I don't know if this is actually working or not. I mean, it must be doing something, right? Okay. Does it actually start all zeros? We have 44 bits of input. That's returning a 0. Oh, 4 pairs. That's a lot. Okay. Has anyone solved yet? No one's solved yet. It's another very reverse engineering day. Okay. So I think I might. Let me just do one more test of this. Make sure that I'm doing the right thing. The low order bits. Yeah, I think I am copying the bits in here correctly. There should be a lot of symmetry in the circuit. I don't really know how to think about that. And also it should be the case that if you trace a path from like the 11th output bit, it does need to eventually, yeah, so what should it actually be? Yeah, okay, it's not that hard to actually figure out what a combinatorial circuit to add things should look like, right? Like you have a previous carry bit from the result of the previous addition, and then you're basically doing a single bit adder with like 3 things: the x at this input, the y at this input, or at this index, and then the carry for this index. And then you need to emit a new carry, and you also need to emit the output thing. So maybe the first heuristic we can try is we can figure out every bit that. Wait, so what does our answer look like in binary? Oh dear. This is like curious pattern-ish. What I was going to say is we can, if Eric obfuscated this a little bit, it's going to be a little annoying. But I guess what we can do, we can look at the kth output bit and sort of see which set of input registers actually touches it. So let's do that. Touched by, and then what we'll do. seems fine. Yeah, I think that's good. Let's play with this. Well, that's not right. It's because I forgot to call DFS. What? Oh. 2 digits. Okay. So that one's fine, clearly. Let's check, like, Z10. Well, that clearly is not working. We don't do that. I completely forgot how to write a DFS. Oh, what am I doing? TS. Okay, maybe I only care about... No, I think I want to do this. Inputs only. Yeah, so I guess I could do... Okay, I kind of don't like that this keeps going off. Okay. Let's take a look. Seems fine. Doesn't appear to be touched by anything that is higher than we need it to. Also seems fine. Is there a way that this heuristic could obviously fail? Yeah, I bet there is. If the modifications are just like local, like it just mixes up the like the operations that it's doing to compute a bit, but not actually like mixes across bits, then this won't show up here, I think. But just in case, let's see. The highest thing is what, 44? In let's check that. We need an extra bit for the output. Okay, this should not be in inits, but this should be. Cool. This all makes sense so far. Yeah, the results of these like the black box calls I was making are pretty weird here. Can I not print this anymore? This is pretty annoying. Where am I printing it? There we go. So, wait, I thought the bottom bit was being set. Wait, what? 4 is not 1, 1 in binary. Why is this not deterministic? That is extremely disconcerting. Huh? What's going on? Oh, shoot. I want my inits. That explains a lot. Okay. G is my current values. Wait, no, I'm confused why that's doing that. Oh, I'm setting G. I should be setting gloc, my local copy of G. Okay, that is pretty scary. Glad that I caught that. feel like I should have seen that non-determinism earlier. Okay, that's correct. So let's try. Let's try some small bits, some like small numbers. Okay, so everything here works. So maybe now we can do. I wanted to be able to shift. See, they're actually 45-bit input numbers because 44 was the max. Sorry, let me think about the alpha oneness here. If 2 is the max, then we'd have 3 bits, and then we would want to consider 1 left shifted by 2. Yep, I think this is right. Okay. Well, I think that just tells me which things are messed up. 12, 29, 33, and 37. It doesn't tell me exactly what's messed up, but it tells me what to look at, I think. So maybe we just like hand inspect these and sort of figure out what's going on. Okay. Let's do from Z12. What are we reaching? So the fact that we're not reaching anything higher than 12 suggests to me that we've just like messed up something here. So let's see. The output for most of these, like Z11, everything up to 11 I think works fine, is an XOR. This is probably true. Yeah, these are all XORs, and Z12 is not. That is very telling. Okay, so NQS is and X12, Y12, NQS. FSF is or of these. Where did JMAR come from? I didn't write that down. This is the one I did not write down. This feels like too much manual work in order for me to like get a good time doing this approach, but I do know it will work, I think. Okay, so maybe I can't say I know it will work if I'm not that confident. QTS is XOR of X12, Y12. QTS is, let's see. And there's probably another XOR floating around here, I bet. What have I not checked yet? JMR and QTS. I have JMR is GPJ and JH. Okay, so we're starting to get back into these. Oh, is there just like a dangling gate that's not touched? That would be really funny if that were the case. Because it does look like let's do a little bit of introspection of these gates. Okay. We have an XOR and an AND. Is that all we normally have? What am I doing wrong? What am I doing wrong, actually? B is equal to x12 in this one. Weird. Okay, well anyways, I feel like there are just some dangling gates here. If it's that would be very simple. So I guess I just need to check for dangling gates real quick. Okay. So which things are not traversed? If okay, nothing. That's not reassuring. Maybe I should actually set this up to print stuff in a reasonable way, so I can think about it better. Or I should just keep smashing my head against this. I have no idea. No, I'll set it up to print stuff in a better way. So from a given register, what we'll do is we will okay. And then okay. Now I can kind of look at this a little bit more reasonably. This is what something typically looks like. Here's another one. Visually, this looks very similar. You're getting first the XOR of these two, and then this is the thing where the carry is coming from. So again, we have the XOR of these. The XOR of these two, we want to XOR with something else as well. But when it comes to Z12, I could use lower max depth, by the way. I think this would be still pretty readable. Maybe. When we look at Z12, it's rather weird. We have an OR going on here. This feels like the... Oh, this feels like the carry. So what is Z13 looking like? This feels like the... No, Z13 looks reasonable. Okay, so what is it getting its carry from? The carry here is this thing. It's the OR of two things. Aha, this is an XOR, not an OR. I feel like this is probably equal to the output of Z12 or something. And Z12 is the carry. That would be my guess. Switch Z12 and FGC. Let's try that. So Z12 and FGC. Let's switch these. This does work in Python for an atomic replace because it evaluates the right-hand side first. And then let's get this thing back and see when things are wrong. What are these prints coming from? Too many prints. This is where it's coming from. The not touch thing I forgot to suppress. Okay, does it look better now? Oh, it looks better now. That's very, very promising. Okay, let's keep going with this. So what were the things? 29, 33, 37. Okay. I don't like that. Why is it not printing anything? Why is it printing nothing? Hello? Oh, it's because my print, it's hitting the print suppression. Oh, come on. Okay. Z29 and Z30. Yep, HKD and... Oh, wait, sorry, not this. This is correct. This is an OR. What is the... Yep, MTJ and the end Z29, I think. Let's make sure that that works. Yep, looks good. Oh, approach is working. I really hope that they all follow this pattern. If it breaks down, then I'll be really sad. Okay, look at the next bit. Oh, Z33 is actually correctly an XOR. So it's not exactly the same problem. Let's consult our reference. What does it properly look like? It's an XOR of two things. One is an OR, the other is the XOR of the two bits themselves. This is an AND of the two bits themselves, so we just need to switch this with the XOR of the two bits themselves. VVM and DGR, I think. No, 33 is still broken. So it wasn't that, I think. It must have been something upstream of those. I'm gonna have to think a little more carefully about this one, I think. I did do the swap, right? I did do the swap. Wait, no, I didn't actually swap them. Oh my god. Okay, that was the fix. Come on. What? Well, that's pretty weird. It's just the AND of these two? Okay. Well, it should be, yeah, this. No. This is correct. This is the XOR of these two. Where does the AND normally appear? The AND bits normally appears like here-ish. So that's, I think, this, DTV and Z38. Sorry, 37. 37? 37. That is not 37. Come on. Okay, it looks good. It looks good. Fantastic. Now we need the output. Sort the names of the 8 wires involved in a swap and then join those names with commas. Okay. I really hope I don't typo here. Rank 12. Let's go. Oh, man. Oh, that feels good. Okay. I really needed one of these on one of the later days. That feels really good. Okay. Sad I didn't make part 1. I was like a little close. What was I was like 135. But honestly, getting number 12 on the second part, that's pretty sick. It's funny how I also had a previous day where I was over 100 and then 12. But yeah, man, that was a tough problem. It was another one of these reverse engineering problems. And yeah, I know a lot of people are not going to like that. I personally kind of enjoy these problems. They are pretty fun. Obviously, my enjoyment is a little colored by the fact that I got a lot of points on the leaderboard. But yeah, I don't know. Just like trying to figure out what Eric did with his input here and figuring out like it's not a general problem you can solve. There's like some special case thing happening here where he probably like modified things in a very peculiar order. So yeah, I guess I'll quickly talk about my approach. The problem itself, you're basically given like a combinatorial circuit. Combinatorial circuit meaning that there's like no loops involved here. You just combine a bunch of these logic gates. In our case, we combine only ORs, ANDs, and XORs. And so if you think about it, you could draw some giant directed graph, directed acyclic graph, because we have no loops here, where each edge is like labeled by the operation. It's actually not quite right. I mean, it kind of is if you represent like gates as nodes. Yeah, if you represent gates as nodes, then I think it's just, you can represent it as a graph if you really wanted to. In some sense, it is like naturally a graph-like structure. But yeah, anyways. So we're given this combinatorial circuit, and the first part just asks us to evaluate it, and then look at the output gates that start with the letter Z. That's pretty straightforward. You just evaluate it. The evaluation here is actually just like a depth first search. So we start at really anywhere, and we like repeatedly just like recurse back up the graph. And if we already like computed a value, then we don't need to compute it again because there's no loops, nothing can change. So it like pretty naturally just like works. Yeah, I guess what is interesting here, not a whole lot. Once you have the output values for every register that starts with Z, in order to like figure out, like I just sorted them. I think it is probably guaranteed that there's no other registers that start with Z that do not have digits at the end. But like Z00 is the lowest bit of the output that we care about, and Z I think 45 was the highest. But yeah, so we just do that, and then this is just me like extracting the bits out of this and stuffing them into a integer. Yeah, so that's part 1. Pretty straightforward, and because of that, you can sort of see that reflected on the leaderboard. Lots of very fast times where you just kind of do it. And for part 2, we are now told that actually this circuit is supposed to add 2 numbers, but it's broken, and there's like so there's a few wires that are crossed. Like there's a few gates that have the wrong outputs. So you might have 2 gates that look like this. One like BKJ equals XOR of Y37 and X37, and FHQ is the OR of RKD and GPM, And maybe it's the case that actually BKJ was supposed to be this one, and FHQ was supposed to be this one. We don't actually know this, or like we don't know which ones are crossed, but we know that there exist 4 pairs of things that are crossed, and nothing is crossed like more than once. So there's exactly like 8 registers or 8 gates that have been like mixed up. And it tells us like find the 8 gates that are causing this circuit to malfunction and not actually add 2 numbers. And once we do find those, just like that's the answer basically. Yeah, so how do you go about solving this? I think in the general case, there's like not really a great approach. You can maybe imagine something like trying a bunch of different random inputs and sort of seeing like where do you, like, you know what the output bits should be, where do they disagree, and sort of go back from there. Part of what I did was understand like what the circuit should look like at a very, very vague level. And then more like manual introspection, as well as like trying some inputs. And that was my general approach. I didn't really have a very concrete approach going into this. But yeah, so I guess like if you think how a combinatorial circuit to add 2 numbers must work, in some sense, probably what it looks like. Here, maybe I'll whip out the draw pad here. Yeah, so, oh, there's my mouse. Cool. So in some sense, what it must look like, so we have this input X. Oh, I forgot to mention this because part 1 didn't tell you about it, but I say it's adding 2 numbers. The 2 numbers it adds are the things from like x00, x01, x02. Like that's the binary representation of the 2 numbers. So let's represent these from the most significant bit off to the least significant bit. And then we've got, like 0, 0, 1, 1, 0, 1. And this would be like x00, x0, I don't need 2 digits here, x0, x1, x2, and so on. And then we have the same thing for y. Maybe it's a number like this, y0, y1, and so on. And if you think about how the circuit must work, assuming you're not like what would you do if you're trying to build a very simple circuit to do this process and not worrying about like trying to obfuscate it or anything? I initially started with the assumption that we're not working with an obfuscated circuit, which turned out to be a pretty good assumption, I think. So what you would do is you would probably build some circuit that is like going to be a black box, or in our case, a red box, and it's going to take in 2 numbers, two bits. And what it is going to compute is it is going to just add these 2 bits, and it will output 2 things. So it'll do the like single digit output. So that'll be, maybe I shouldn't call these X or A and B. I should call them X and Y perhaps. But we'll output C, and then we'll also output, it's also out, sorry, I don't need C for that. I'll say R for the results. And the idea is that we'll take in this bit, and we'll output like a carry that will carry on into the next computation, as well as the output of this, log position specifically. Then you realize that in order to do this at the second location, you actually are going to need a carry as an input as well. So really it'll be like a 3-bit adder. This is still fine because if you add 3 single bits, the largest result you can get is most going to be 2 bits. Like we only need to ever worry about 1 carry bit. And like what will this circuit actually look like? Well, you can think about it. I chose not to think about it during the solving process here. And so, sorry. Yeah, so I chose not to think about it during the solving process here. And let me just fill in this box. You don't necessarily need to know what it looks like. You can sort of like pattern match a little and like look at the differences between, like you can kind of figure out what the box looks like by just going to some bit here and like actually looking at the gates by hand with your eyeballs. But if we wanted to sort of think through it, what is it going to be? Well, the result bit is going to be set if exactly an odd number of these things are set, right? So either if all of them are 1, then this is going to be 1, or if exactly one of them is 1, then this will be 1, and otherwise it'll be 0. That's actually a pretty simple operation to express. It is just the XOR of all 3 of these things. So I don't know if I really want to like fully draw out this entire gate, but it will look something like this. And yeah, and that'll just be the R output. And then for the carry, that one's a little trickier. We kind of want to count up how many bits, like if at least 2 bits are 1, then the carry is going to be set. Otherwise, it won't be set. And I think that's going to look something like maybe you do an AND. You're going to do some combination of ANDs and ORs, I suspect. I'm not actually going to go through the exercise of working this out here, but like you can figure this thing out. And roughly what you realize is that this is going to be a block of these things tiled. So we're going to have 1 for each output position. And we'll sort of be like chaining in the, oops. My draw pad is a little messed up. Okay, there we go. We're going to be chaining in the outputs into each one. So like the carry from this, carry output from this will go into the carry into the next one, and so on and so forth. And roughly the approach I took here. So the first thing I wanted to figure out is like which bits are actually messed up. I tried a bunch of small numbers, and it worked just fine for a bunch of small numbers. So like evaluate on 37 and 50, and it adds this just fine. So this suggests that most bits are like doing fine, but probably some of the higher order bits are not doing fine. Now, how do you find out what the higher order bits are without like trying every number? Trying random numbers could work, but it's like a little bit weird. A thing that you could try is you can try just adding 2 numbers that both have a single bit set. And you can try varying the position of the bits that are set. And sorry, 1 second. Yeah, so I fed in a bunch of the like singleton, like things with single bit set. And I sort of ask like for which bits being set is the output not matching. And that was this thing I wrote here. And this like very quickly let me identify which bits were messed up. And I saw exactly 4 bits that were messed up, and that was like a pretty promising result. From there, what I did was mostly sort of like squint really hard at those bits, squint really hard at other bits, and sort of see like visually pattern match and see what the difference is. I think for one, I should probably comment these out in order to like get the behavior back. But yeah, I think, let's see. So the 12-bit was messed up. If you look at Z10, you'll see that, yeah, so it's actually the XOR of these 2 things. This is surely the carry bit, and this is surely, or like, this is just the XOR of these 2 things. So it's doing exactly this operation, right? We can like sort of recognize that. And if we look at Z11, it looks very similar. If we look at Z12, we'll see, well, for one thing, Z12's output is an OR. So we just know right away that that's not right. It like really should be an XOR. And then what else do we notice? Yeah, so there is the XOR happening here in like QTS, but we don't see an XOR of QTS with something else. I guess a few things we could have done. Well, we could have looked at what uses XOR as an input. I did not end up doing that. I ended up mostly doing like check the next bit. So a thing I also thought about was maybe it's possible that the 2 wires that were crossed were something like this one, like the output of this and the output of this. And that actually cause, yeah, I think if you told R that it was this output and you told this thing's input that it was R, it would probably be fine. Anyways, that would cause you to have like dangling gates that would like never get reached during evaluation normally. So I did check that actually quite early, as I checked for what I'm calling dangling gates. I didn't find any, which sort of that guided me towards the approach of Just look at the next bit. And I look at the next bit, and you'll see that the next bit here like does look reasonable. It's the XOR of these two things. One is this, the other is the carry. But oh, look, now this carry looks rather peculiar, right? The carry is not normally an XOR. The carry is normally like an OR, right? And this thing was an OR, when it should have been an XOR, and this thing is an XOR. Like you can reasonably make the jump from here that FGC and Z12 are just switched. Was that actually correct, what I did? Yeah. And then another fun thing is you can actually just try and swap them and see how this metric does. Like this thing where you're trying a bunch of different inputs. So that is exactly what I did. And it worked, and I just kept doing this process. It's a little different for some of them. Like they're not always switching the actual Z with some intermediate. Sometimes, like I think there was 2 intermediates that were swapped for the third one. Yeah, but with like enough squinting and pattern matching, you can definitely like figure it out. And yeah, that is all I have for day 24. How's the leaderboard doing? Let's take a look. We are only halfway full in the leaderboard. That's pretty wild. But yeah, I mean, it is a tough day, and very like reverse engineering-y. So lots of manual work involved. Yeah, let me see. Where does this take me on the global? I am 77. Okay. Well, I'll definitely finish in the global this year, but I'm not finishing in a particularly high spot, sadly. But yeah, I think that's all I have for today. So I will see you tomorrow.